If you are doing this from home, you should have watched a YouTube video, just a real quick one about the different types of radioactive decay. If you haven't already done that, go back to the assignment in Canvas and watch that video. Now, if you're just watching this because you want a repeat of what we did in class, you probably don't need to watch that video. You could just follow along with your note sheet. This section is on radiometric dating, which is a type of absolute dating, putting exact numbers onto the age of rock layers, fossil types, used for different things in different sciences. But in geology, we're generally trying to figure out the age of rocks or fossils. Just to remind everyone, when you're talking about an atom, you have a nucleus that has a number of protons and a number of neutrons, and these should be balanced. And then you have electrons, which are smaller and have a negative charge that kind of hover on the outside in these, let's say, shells on the outer edge. Now, if everything's balanced, we have a nice, normal, typical atom, let's say, of carbon. Carbon should have a total atomic number of 12. Sometimes, though, it'll get extra neutrons. In that case, we have what's called an isotope. An isotope is a version of an element that doesn't have the typical number of ingredients. So its mass or its charge is slightly off. The parent isotope is also known as a radioactive element. What this means is that we're dealing with an element that is not stable. It's an element that may need to shoot off some of its extra protons or neutrons in order to reach its ideal atomic mass, may need to capture or give off some electrons in order to become a stable element. The radioactive element may have some extra protons, neutrons, or electrons. Notice the radioactive element is called the parent. That's because it starts off as radioactive, but eventually it may stabilize into what we call a daughter. A daughter product is stable and safe. For example, you've probably heard of uranium. Well, uranium will eventually become lead if given enough time. Uranium's highly radioactive, it can cause a lot of trouble, and the lead that it becomes is stable. Now, in the daughter, we are going to write the stable element. When you go to get x-rays, they will put a lead apron on you because lead is so stable, it will block the radioactivity from getting through the apron to protect your soft parts. So like if you're going to the dentist to get your teeth x-rayed, they'll put a lead apron on you. Lead is safe, uranium's not. Lead can start off as uranium. Uranium can become lead if you give it enough time. So the stable element, this is the end product of radioactive decay. And that word decay is the word we use to describe the process under which the radioactive element gets rid of its extra parts. They kind of shoot off into space, they're invisible, you don't see them. If you have something called a Geiger meter, you can record them. But otherwise, this radioactive decay is an invisible process. So for example, here I have a piece of diorite. This diorite potentially has radioactivity. Most rocks do have some small level of radioactivity. As we're sitting here, it could be giving off extra electrons or neutrons or protons and stabilizing out, but it's not changing size or shape or color or anything. It's just undergoing this invisible change that we call radioactive decay. It's becoming more and more stable, like our daughter products. An example you may hear of in anthropology class, carbon-14. Carbon-14 is used to figure out the age of artifacts from ancient civilizations like the Mayans, the Aztecs, the Incans, and we can figure out how much carbon-14 we have left and it will stabilize into nitrogen-14. So we can figure out how much nitrogen-14 we have now to figure out how old the artifact is. In fact, that's going to be a problem on the back of the page, and I'll show you a little video that explains it. Now, the last of our vocabulary terms is half-life. The length of a half-life is the amount of time it takes for half the parent to stabilize out. So the half-life is the length of time for half the parent to become stable daughter. And the length of the half-life is different for all the different isotopes. So carbon-14 has a pretty short half-life, 5,730 years. That's not short to you and me, but uranium has a half-life of 704 million years. So that's a big difference between 5,000 and 700 million years. Biologists and chemists will use isotopes that have very short half-lives if they want to watch a reaction in real time, like through a microscope. Astrophysicists who are trying to figure out the age of the universe and stars will use isotopes with very long half-lives in the billions of years. Alright, so we're going to make a note sheet here. You'll use this note sheet in order to answer some problems, do some practice in the future. Look at this this diorite again. Imagine that this is one fresh rock. At this point in time, it's 100% radioactive. Alright, sorry about that. Some announcements there during passing. So imagine this got 100% radioactive isotopes when it's fresh. No time has passed at all. No half-lives. So we're looking at a parent fraction of 1 over 1. It's 100% parent. It is 0 over 1 daughter fraction because it's 0% daughter. It's all radioactive, and the ratio is 1 to nothing. For every one parent, there's no daughters, because that's the beginning of time. That seems silly, but we're working on a pattern here. So we start off at the base, right when the rock is new. Over one half-life, half of the parent is going to stabilize out. So now we have half parent, half daughter. So imagine we started with this as our rock, because it's easier than looking at this right here. After one half-life, half of it stabilizes out. Now, it's not truly the bottom half, but it's easier if I do it that white is radioactive, purple is stable. In reality, it would be bits and pieces from all around that are stabilizing out, so it would be more speckled like this. We just wouldn't see any change. It's an invisible change. So we have half stable, half radioactive, half parent, half radioactive, half stable. Our ratio to now 1 to 1. 1 part of each, 50% parent, 50% daughter. After another half-life, half of what was left is stable. So now we have 4 parts total. 1 of the 4 parts is still radioactive. 3 of the 4 parts is stable. Our ratio is 1 to 3. We're down to 25% parent and up to 75% daughter. So you see, the percentages always equal 100%. The ratio is always what the numerators are. If you add the two fractions together, it will always equal 1 whole. If we add our ratio together, it equals the denominators. So there's a lot of patterns here. If we keep going, now we have 1 part parent to 7 parts daughter. So we have a 1 to 7 ratio, which means there's 8 parts total. So we're at 1/8 parent, 7/8 daughter. Our percent parent's down to 12.5. And our daughter's down, or up, add that 12.5 over, so we're up to 87.5% for our daughter. So by now you should be seeing a pattern for our denominator. We multiplied by 2 every time. So the next is going to be 1/16. And then 1 over 32, 1 over 64, 1 over 128. And finally, if we double 128, we are at 256. So take a minute. I'm just going to pause it, fill out the rest of the chart. You should do the same. All right, so I expect that you got the fractions no problem. 256, 255, 256. Our parent-daughter ratio, 1 to 255. Over in the percent, it's okay if you're copying mine. I kind of rounded a few of these. My point is you don't get down to 0. You don't get up to 100%. It will probably take about 11 half-lives to get down to 0. This decimal would keep getting smaller and smaller until it really didn't count. But we're only going up to 8 half-lives here because this is as far as I'm going to ask you to go in our problems. And that's plenty far for our purposes. Looking at a fraction of 1 over 256, that's a pretty tiny amount. So we're going to use this information. If you skip question number 1 and go down to 2, 3, 4, it's just a matter of can you read the chart. So here it says determine the amount of daughter present if the following amounts of parent were found in a decaying fossil specimen. So let's say we have a fossil and we find 1/8 parent. We don't know what fraction of daughter we have. You might just know off the top of your head, but if you didn't, go up here, find 1/8 parent, 7/8 daughter. You could do the rest of these. Pause it, take a moment, finish the rest of these. Next, it says determine the ratio of parent to daughter for the following fraction. Alright, so we have 1/8 to 7/8. So if we look at that, you might remember just to take the numerator, or maybe you really can't remember. So go up here, we have 1 to 7 ratio. And then finally, for the last part, it says determine the number of half-lives for the following parent-daughter ratios. So we have 1 to 7. We just did 1 to 7. Up here, 1 to 7 is 3 half-lives. So we have gone through 3 half-lives. For now, that's good enough. Eventually, I'll show you in class how to figure out that number 3 without even using the chart based on this ratio right here. So, pause the video, take a moment, fill this in. If you have any questions, let me know, but it's really just a matter of reading the chart above. The last big thing we have to cover is the equation for finding the age of a sample using radiometric dating. So I'm going to scoot back down. The equation is pretty simple. We're just multiplying 2 numbers together, but I do want you to write the formula out in words. The age could be the age of a rock, like our granite. Could be an age of a fossil, dinosaur bone, person bone, who knows. It is going to be the number of half-lives times the length of 1 half-life. Now the reason I wanted you to write that out in words is because if you use 1 over 2 for half, all of a sudden you might start multiplying by fractions, and I definitely don't want you to do that. Now the number of half-lives is always going to be somewhere between 1 and 8 for our purposes. The number of half-lives comes from this chart over here. So you would use clues like you have 15/16 daughters. How many half-lives? 4. Or you have a ratio of 1 to 63. How many half-lives? 6. It could even be percentages. Like you have 25% parents. How many half-lives? 2. So we're reading the chart using the clues. The length of a half-life is going to be from a chart. It's going to be given to you. So you're multiplying two numbers to get the age of whatever you're talking about. A rock layer, a fossil, an individual rock, a mineral. We're going to do one sample problem together on the back. On the back, there's a table for you to look at. Here's the parent, carbon-14, becomes nitrogen-14. It takes 5,730 years to go through one half-life. Uranium-235 becomes lead-207, half of it over 704 million years. So this is a chart. Here's your parents. Here's your length of a half-life. We are going to do number 6 together. It says if the amount of carbon-14 found in a fossil is 1/8, how old is the fossil? Remember, our formula is that the age equals the number of half-lives times the length of a half-life. So based on this chart, we can figure out our length of a half-life for carbon-14 is 5,730 years. We have to multiply that by the number of half-lives. We are given the fraction 1/8. So we go back here, we look at 1/8. 1/8 goes with 3 half-lives. So we have 3 half-lives times 5,730 years. And we put that in your calculator, you are going to end up with 17,190 years. Not too bad. You're going to do the same thing for the others. Here we have a fraction of 1/2. Figure out how many half-lives that is. Figure out the length of half-life for uranium-235. They're all going to be similar, except for if you look at the very last one, this one says, what time period did the sample come from? So once you figure out the age of the sample, you will need to look up what time period was going on that many years ago.